So we've been talking about the translation of a program to its SSA form, and the first step in this translation was the computation of dominance frontiers. The second step, which I'm going to discuss in this module, is the placement of trivial phi nodes. So consider this assignment statement at location x to variable v colon equals something, and let's say y is in the dominance frontier of x, which means y is the first node which is not strictly dominated by x if I do a depth first search traversal starting at x. And if y is in the dominance frontier of x, that means that there must be another definition of variable v that is potentially reaching y, because y is not strictly dominated by x. Now when I say another potential assignment to v, I also include the initial values of v which must be present at program entry. And so either there is an assignment on this other path to y, or the original value, the initial value of v is flowing on this other path. In either case, I need a phi node here. Now, I'm going to stage this placement of phi nodes into two steps. The first step, I'm going to place a trivial phi node, which means I'm going to add an instruction which says v is assigned colon equals phi v comma v dot dot dot, where the number of arguments to the phi function depend on the number of incoming edges at the node y. So this is also called a trivial phi node because it's a no-op instruction effectively, and later on we are going to rename the variable so that it becomes in SSA form. The program becomes in SSA form. Also notice that I'm only going to place the phi nodes at the dominance frontiers, and this will satisfy our requirements for a minimal SSA, which is the minimal number of phi nodes are placed for all the variables. So once again, if I see an assignment, for example, v colon equals something, then at a node x, then I look at the dominance frontier of x. If y belongs to the dominance frontier of x, for all such y, I add a trivial phi node, which looks like as shown in the slide. Not just that, we need to do this transitively. So once we add a trivial phi node to y, and let's say z was in the dominance frontier of y, then I need to similarly add a trivial phi node to z. And this is because the phi node that I've added at y is basically treated just like another assignment. And so just like we placed a phi node at the dominance frontier of x, which was an assignment, because now y contains an assignment, so we are going to place a phi node at the dominance frontier of y, which in this example is z, and so on. And I will keep doing this until I place, until I have placed the phi nodes at all the requisite places where the phi node is required by this dominance frontier transitive relationship. The other important thing to note here is that once I place a phi node at a particular node, then I do not need to place another one. So there's only, for a single variable, there can be at most one phi node at any node, because after all, a phi node is basically just at the very beginning of the basic block, and for every variable I need at most one phi node. So for example, if z was also in the dominance frontier of x, then there will be only one phi node that will be placed in z. There won't be two phi nodes by virtue of being in the dominance frontier of both x and y. We will only place one phi node and not two phi nodes in this case. Finally, I've shown this placement of trivial phi nodes for a single variable v, but I need to do it for each and every variable present in the program. And the way I'm going to structure the algorithm is I'm going to do this separately for each variable. For example, I'll do it for v1 first, place all the trivial phi nodes for v1, then I'm going to place all the trivial phi nodes for v2, and so on. And so this can be done separately and independently for each variable. Okay, so the high level algorithm for the placement of phi nodes looks like the following. The place phi function, which places phi nodes in the program, trivial phi nodes, takes as input a program. And for each variable v in the program, it changes the program by placing the phi nodes for the variable v. And so it gives you a new program, and this iteratively continues until we have placed phi nodes for all the variables in the program v. So now I'm going to look at more deeply into this function place phi for var, which takes as input the program and a particular variable, and I'm supposed to place the minimal number of phi nodes for this particular variable. So we have already seen what the algorithm is going to look like. I'm going to basically look at all the assignments of V and look at the dominance frontiers of the nodes which contain those assignments, and then place phi nodes in those nodes which belong to the dominance frontier. For this, I'm going to maintain a work list, and this work list will be the nodes whose DOMF or the dominance frontier needs to be examined. For example, if a node contains an assignment to the variable V, then its DOMF needs to be examined, and so the work list will contain contain that node X which contains an assignment to V. And as the algorithm proceeds, the work list more nodes may be added to work list, because after all we need to do this transitively. So if I add a phi node to a particular node, say Y, then all the dominance so I need to consider that new phi node as a new assignment, and now I need to look at the DOMF of Y and so on. And so I'm going to maintain this as a work list, and when I pick something from the work list, I'm going to remove it from the work list. But sometimes when I add phi nodes, then I'm going to potentially add to the work list. Similarly, I'm going to maintain a set called considered already, which will be the nodes that have ever been through the work list. So if I have already considered a particular node X and I've already examined the dominance frontier of node X, then I don't need to examine it again, because after all, I only need to place phi nodes at most once for any dominance frontier node for that particular node. And so once I've considered a node, I don't need to consider it again. And I'm going to maintain what I've already considered in the considered already set. In one way, considered already are the nodes that have ever been through the work list. So anything that has been through the work list, maybe it has been removed, it still remains as part of the considered already. So as the algorithm proceeds, work list may shrink and grow depending on what are the dominance frontiers where the phi nodes have been added. But the considered already set only grows because it's a cumulative set of all the nodes that have ever appeared in the work list so far. And finally, I'll maintain a set called has already, which are nodes that already have a phi node for the variable in the program. Because these nodes already have a phi node for the variable in the program, I don't need to place another phi node in those nodes of the program. And that's because of the property that I need at most one phi node for a given variable at a particular basic block. So this is my high-level pseudocode of the algorithm. I initialize the work list, which I'm calling W, with the nodes with assignments to V set to true. So initially all the nodes or the basic blocks which have assignments to V, they belong to the set W. So to represent the fact that these nodes belong to the set W, I just say that which nodes have their value set to true, or it's a map from nodes to Boolean values, and a true value indicates that it belongs to the set, and a false value indicates that it does not belong to the set. So W is basically nodes with initialized to the nodes with assignments to V. Considered already, recall, is the cumulative set for the work list, and it is initialized to everything that W has been initialized to. That's the initial value of considered already. As the algorithm proceeds, considered already will keep growing, as we have already said, but work list may shrink or grow depending on what the dominance frontiers we see. And has already are the nodes where a phi node already exists for this particular variable V, and it has been initialized to empty. So far, initially there is no phi node anywhere. The algorithm proceeds as a fixed point iteration, where we say that while W is not equal to empty, so while the work list doesn't become empty, we pick one node from the work list. So take X from where Wx is true and set Wx to false. So that's the shrinking part of the work list. And for each Y belonging to the dominance frontier of X, place a trivial phi node at Y if it does not already exist at Y. So if a trivial phi node does not already exist at Y for this variable V, then place this trivial phi node at Y. Set has already for Y to true, because now there's already a phi node in Y. And if considered already, if Y has not been considered already, which means Y has not already gone through the work list once, then add Y to the work list and also add Y to considered already. So this is the transitive step. So if I've added a phi node to Y, I also potentially need to add it to the work list if it has not already been added to the work list, if it has not been considered already. And so this is my high-level algorithm to place phi nodes. It's a fixed point algorithm that maintains a work list, maintains a cumulative considered already set for the work list, and it has already set to basically ensure that we don't place duplicate phi nodes. and then it just looks at each node from the work list, looks at the dominance frontier and places a phi node if it does not already exist there, and adds y back to the work list if it has not already been considered. Now I want to point out that this algorithm that I just mentioned is for minimal SSA, but recall that we also discussed another form of SSA, which is a pruned SSA, which is a stricter requirement, which says that you place a phi node only if the variable v will be used in the downstream nodes, or in other words, if v is live at y. And so just a simple change to this algorithm will also can adapt this algorithm of placing phi nodes to a pruned SSA. You just need to check whether v is live at y or not. And you can run a liveness analysis a priori, and recall that the liveness analysis only needs to be a conservative liveness analysis, so it doesn't need to be fully precise or anything like that. And depending on how precise your liveness analysis is, you may be able to reduce some of the phi nodes in your program for the pruned SSA representation. Okay, so I'm going to run through an example with our algorithm to see how this works. So let's say this is my program. It has these assignment statements to v, and I'm looking at v and placing phi nodes for this variable v. And there are two assignment statements, one at PCX, another at PCW. And then this is the rest of the control flow graph. I'm also showing the dominance frontiers of each of those nodes. For example, dominance frontier of x is y because there's another incoming edge to y. Dominance frontier of y is z because there's another path coming to z from somewhere. Dominance frontier of z is u and x because there's a back edge going out from z. So dominance frontier of z is x, includes x and also includes u. Dominance frontier of u is empty because probably it's just going to exit. And dominance frontier of w is z. Now when I initialize my algorithm, I initialize my sets. My initial work list is basically the set of all assignments to v, which is x and w. So that's my initial work list. My initial considered already set is anything that has gone through the work list, which is also equal to w, and has already is empty. Recall this was the initial state of our sets in our algorithm. Now I'm going to take one by one a node from the work list and look at its dominance frontier and place phi nodes in those dominance frontier and potentially add those nodes back to the work list and to the considered already set. So let's say I pick x first. So I pick x first and the dominance frontier of x is y. So I place a phi node or a phi function at y. I add y to has already, and this is the state of my sets at this point. Now the next thing I want to do is I want to check whether y is already part of considered already or not. It is not, in which case I should add y to the work list. And so that's my next step. I add y to the work list because I want to consider this assignment and also look at all the phi nodes that need to be added by virtue of this phi function added at y. So my new work list is y comma w, and my considered already set also includes y now because of by virtue of y being added to the work list. Now once again I need to pick up some node from w. So let's say I pick y and I look at the dominance frontier of y, which is z. And I'm going to check whether z is already part of has already. It's not, and in which case I'm going to add a phi node to z. So that's my next step. I pick y, I look at the dominance frontier of y, and that's z. I add z to has already, and I add a phi node to z. Now once again I check whether z is a part of considered already or not. It is not, in which case I should add z back to the work list. So that's my next step. I add z back to the work list, and also I add z to considered already. Now I need to pick something from the work list and examine its dominance frontier. This time let's say I pick z and I examine the dominance frontier of z. The dominance frontier of z includes u and x. So I'm going to place phi nodes at u and x and add u and x to the has already set. So let's see that. So indeed I picked z and I added phi functions to u and x, and I added u and x to has already. Now both u and x may be part, so now I also need to transitively add u and x to the work list. Before that I need to check whether u and x already belong to considered already or not. So u does not belong to considered already, but x already belongs to considered already. Because x already belongs to considered already, I don't need to add x to the work list. This is because I've already considered x and I've already added its phi nodes, its dominance frontiers I've already added 5 nodes at X's dominance frontier. And so I don't need to consider X again, but I do need to consider U again. So I'm going to add U to the work list and to considered already. And so I'm going to add U here, and I'm going to add U to considered already, and I'm going to continue my algorithm. So in this case, I'm going to, let's say, pick once again one of the nodes in W. Let's say I pick U. And when I pick U, then I'm going to look at the DOM-F of U, which is empty set, and I'm going to add 5 nodes there. But the DOM-F of U is empty, so I don't need to do anything. So I'm just going to remove U, and I'm going to add, so nothing needs to be done for U, and so has already, and everything remains the same, just that U gets removed from the work list. And now I go back to the work list and pick the next node. And in this case, now I have only one option. Let's say I pick W. I pick W, I look at the work dominance frontier of W. It has Z already, Z already has a 5 node. So Z is in the dominance frontier of W, but Z already has a 5 node. So I don't need to do anything. And that is the end of my algorithm. And I don't need to, and I've reached an empty work list. So I've reached a fixed point. And these are the minimal set of 5 nodes that need to be added in the program that I just showed you. Okay, so what is the running time of this algorithm? And to be able to reason about the running time of this algorithm that places trivial 5 nodes in the function, I need to first define some quantities which depend on the on which the running time depends. So one of the quantities is what is the number of assignments in the program. And notice that as the algorithm proceeds, it adds more assignments. It adds more 5 functions, trivial 5 functions to the program. So there's one quantity which is the number of original assignments in the program, which I call A_orig. And if I sum the number of original assignments over all the basic blocks X, then A_orig is summation over X, A_orig X. So where X is a node in the CFG or a basic block in the CFG. So this is the number of original assignments. But our algorithm actually has a runtime that's proportional to the number of final assignments in the program. And the final assignments in the program include all the original assignments and the extra 5 functions that we have added. And so the number of final assignments is represented as A final, which is again summation over all the basic blocks AX final. So if for every basic block X, I can compute what is AX final. And AX final is nothing but AX original plus all the 5 functions that have been added to X. So in other words, AX final equals AX orig plus AX phi. Let's look at this equation AX final equals AX orig plus AX phi in more detail. AX orig is the original number of assignments in basic block X, and AX phi is the number of assignments added due to 5 nodes in basic block X. Now the number of assignments, number of 5 nodes that may be added can be as big as the size of the entire program A_orig, which is the summation of over all the basic blocks AX_orig. To see this, consider the number of 5 nodes that can be added to this basic block. The number of the 5 nodes that are added here may be due to all of the other basic blocks X, Y, Z, and W. And so the number of 5 nodes added in a single basic block can be as large as the size of the original program. In other words, AX final can be between AX orig, which is because of this, if there were no 5 nodes added, or and can be less than A_orig. So it can AX final will be greater than the lower bound will be AX orig, and the upper bound will be the total number of assignments in the original program, because that's how big AX orig plus AX phi can be, because we already saw that AX phi can be as big as A_orig. And so, if you sum it up, that comes out to be roughly A_orig. And this is just for a single basic block, the number of final assignments in a single basic block. If I sum it up over all basic blocks, then that becomes A final, and I sum it up over all basic blocks, so that can be as high as, roughly speaking, A_orig square, because the number of basic blocks is roughly proportional to A_orig. And so you multiply A_orig with A_orig square, that's the upper bound. The lower bound is summation over all the basic blocks for AX_orig, which is just A_orig. And so the total number of final assignments can be quadratic in the number of original assignments in the program. And we're going to use this later when we talk about the running time of our algorithm. So please keep this in mind. So if I want to analyze the running time of my algorithm, notice that this statement here, which is take X from WX equals true, is executed for every node X where there exists an assignment to a variable V. And the number of assignments to a variable V changes as the program executes. So this statement actually executes as many times as there are final assignments in the program, because after all I execute this also for, I add to the work list also those assignments which are 5 functions which are added as a consequence of the algorithm. So this statement here is executed a final times, where recall a final is basically summation of over all the basic blocks, ax, the number of final assignments in that basic block. So this statement is executed a final times, and for each such time that this executes, the number of times the inner loop, which is this for each y belongs to DOMF, is executed for the size of the DOMF of that particular node. So this statement, this inner loop statement, or the inner loop logic, is executed ax final into the size of DOMF x. So for any basic block x, the number of final assignments in x multiplied by the size of the dominance frontier of x. That's the number of times this statement is executed for a particular basic block x, and we sum it over all the basic blocks x. And that's the number of times this inner statement is executed. Now, what is the typical size of ax final? Well, it could be as big as the program size. What is the typical size of the dominance frontier of a basic block? Well, depending on the program, it may be constant size, or it could be as big as the program size itself. We're going to see how how we can reason about how big a dominance frontier can be. But this quantity here can be anything from linear to quadratic, and we're going to characterize when it's linear and when it will be quadratic. But the good news is that it will mostly be linear size, linear in the size of the program. This quantity can also be written in a more succinct form as a final into the weighted average dominance frontier size, where the weighted average is based on the average of the dominance frontier size for the different weights, where the weights are dependent on the number of assignments in that node X for whose dominance frontier we are looking at. So this is executed a final times weighted average df size. A final can be between linear and quadratic in the size of the original program, as we saw earlier. The weighted average df size can be constant size for a given basic block, or can be as high as the number of basic blocks in the program. So it can be between constant and linear size in the size of the original program. And so the product of both can be between linear, if a final was linear and weighted average df size was constant, to cubic if a final was quadratic and weighted average df size was linear. So the overall running time can be between linear and cubic.